Okay, for this tutorial, I want to show how to calculate Clebsch-Gordan coefficients using the QM-Maxima package. Now, what are the Clebsch-Gordan coefficients? So if we have two particles and they have, in the JM representation, they're in the state J1M1 and J2M2, then those two particles can be represented in terms of a total JM state, capital J and capital M here. And so what we want to do to find the Clebsch-Gordan coefficients is to start at the top of the ladder for both particles. We'll calculate then what the J total is and what the Z projection is at the very top of the ladder, and then we'll step down in the two particle states and also at the same time step down in the total JM state, and by equating those as we step down the ladder, then we can compute the Clebsch-Gordan coefficients, which are just the overlap between the total JM state and the tensor product state here. So now there is a Clebsch-Gordan coefficient calculator within Maxima that will compute this for this quantity for you very simply by just using the general formula for the. There's a general formula that you can derive for this amplitude here. But what we want to do with this package is more educational and so pedagogical, if you will, and so we can calculate it by stepping down the ladder. So the first thing to do is to load the package and load the WX Lisp file as well, since we're using WX Maxima. And then we want to construct the top rung of the ladder. So for this particular example, we'll use two particles, one of spin 1/2 and one of spin 1. And so when we make our TP ket, our tensor product ket, we use those two top states. And so we're going to call this top state JM top, and that's our TP ket. Now we want to calculate the total J squared for this top state. And so when we calculate J squared for this JM top ket that we just created, tensor product ket, then we end up with a coefficient now, or a common factor, that's 15/4 times h bar squared. And we can calculate the J. This must be equal to J times J plus 1. So there's a convenience function called getJ, and if I just give it the coefficient 15/4, it solves that equation J times J plus 1 equals 15/4, and it gives us J equals 3/2. So we know that the top state and the total spin is 3/2. So the very top of the ladder in the total JM is 3/2, 3/2. And we can confirm that because J total Z for this JM top state is 3/2 h bar. The common factor is 3/2 h bar. Okay, thus we know that if we write the total JM, it's 3/2, 3/2. And now we can just walk down the ladder. So if we look at the total JM state, which is this 3/2, 3/2, and we calculate J minus, then we will get square root of 3 times h bar, and we're taking J minus of this state, so we're going to lower the M value by 1, so it goes from 3/2 to 1/2. And if we take our original tensor product ket and lower its state, so we take J total minus, that's for the tensor product, then we end up with two tensor product kets, where we've lowered, in this case we've lowered the 1/1 ket, and then in this case we've lowered the 1/2 1/2 ket. Now this, because we've taken J total minus, notice I have some coefficients here. I've got a square root of 2 h bar for this tensor product, and then I've got a common factor of h bar for this tensor product. So when we equate the 3/2 1/2 state, which is what we stepped down from the total JM state, that has to equal, then I can divide by 1 over the square root of 3 times h bar times the J total minus of the JM top state. Okay, so they must be equal because we started at the top rung of the ladder and we stepped both of them down by 1. So once we compute what this state is, so 3/2 1/2 has to be equal to, as I said, 1 over the square root of 3 times h bar times this J total minus of JM top. We can call this new ket the K 3/2 1/2 in terms of the total JM. So what we've done in this step here is I've used the function tensor product scalar multiplication. So we're multiplying the tensor product by this scalar, and then this is the ket that we're multiplying it by. So that gives us this is the ket, and it has there's two pieces to this ket. It's got this piece and the second tensor product piece. So if we took then the overlap with 3/2 1/2, the total JM state, then we can just peel off the coefficients here. So we have our first coefficient, our first Clebsch-Gordan coefficient here is the square root of 2 over 3, and then this one will be the square root of 1/3. And then you can do this process again by just stepping down the next rung of the ladder. So you can take the previous state that we had just computed and step down from that, and then step down the total JM state to give this 3/2 minus 1/2 state. And then we can then compute the next. This is the next rung of the ladder, and then we can peel off those Clebsch-Gordan coefficients. And just continue until you get to the bottom rung of the ladder. So that is how you can compute the Clebsch-Gordan coefficients in the QM-Maxima package.